Okay, let's see. This part maybe already talked by Ajahn Lin, no? A lot already. Okay, did he emphasize on this? Okay, let me go through very briefly then. Everyone knows already that the ionosphere is one of the layer. It's not even called atmosphere. When we talked about atmosphere, we talked about lower altitude, no? So the ionosphere is well known. It's been studied for a long, long time since 1960s, because during that year they utilized a lot of communication, in the ionosphere. For example, in the HF communication and all that. So there was a lot of study, and it slowed down until the early 2000. It became active again. People are more interested, and so on, mostly because of GPS, GNSS. So people come back and look at it. So the altitude is roughly from maybe 50 kilometers all the way to, say, what you could say 1,000 kilometers. You could say 10,000 kilometers. Some people say 20,000 kilometers. So up to you. But basically, on the x-axis, if you take a look, these are the ion electron density. They tend to increase slowly, from the very low altitude from 50-60 kilometers, and then it starts to peak at 250-300 kilometers, and then it starts to slow down. So normally we call this part as bottom side, and this part as, let me use the pen now. And so here, around here, we normally call it as bottom side, and the higher part we call top side. Okay. So people who look at this specifically, or they try to observe the electron density, the ion density. Some people focus more on bottom side. Some people focus more on top side, and the techniques are very different. What they use, right? Some people also look at in situ. For example, there are some LEO satellites that are launched in here. So they measure inside this layer. So we call in situ. The slides are already given to you in Google Classroom, so you can use it. Okay. And but of course, this type of curve, which is called electron density profile, I mean, it just moves up and down, and it's very dynamic, right? So during daytime and nighttime, they are not the same. And so from the side view, there are this electron density, and there are sometimes there are some disturbance that occurs. So they are very, very dynamic, and so on. And because they are ionized, right? Electrons or ions, they are ionized. So that means that these electron or free electrons, you can say, they are mostly they are from this type of effects of EUV or X-ray, and that's how they ionize. So that's why this plot is very important. So generally, have you seen this plot before? Okay, so I'm not gonna go very deep, but basically you focus, you find that in general they are more neutral ions than ionized ions. Okay, so the ionized part is lower, smaller compared to the neutral part. Okay, so even with the ionized species, the background ions, background neutral ions, have so much more density than the ionized part. So it's not just the ionized part that that occur at this layer. And specifically, if I look at oh my god, the screens are small for me. Yeah, I need a magnifying glass. No, it's okay. It's okay. No, no, no need. It's for you. I can zoom in. No, don't worry. I can zoom in. Yeah, but I mean, if you're specifically interested, for example, for me, I will try to look at 250 kilometers to 300 kilometers, where we have the bottom side, we have all the bubbles occur, disturbance occur around here, right? We know that in the ionosphere, in the atmosphere in general, you have oxygen dioxide, you have helium, you have nitrogen, and all that. So when you look at the ions around this region, for example, so you find that so there are lots of um, there are lots of N plus, for example. There are lots of NO plus. There are lots of oxygen, right? And there are lots of O plus, right, at this altitude. So these are the three, four ionized species that often we talk and we look very interested. Okay. Um, so so you will not be surprised that in some study, people try to look at the ratio between this type of NO, you know, um, ratio. Okay, if some slide you have already seen, please tell me, then I can go faster. Oops. Okay, this you probably already saw, have seen before, that during daytime, because of the ionization, some of the ions, some of the neutral ions, they become ionized. For example, the oxygen, or it ionized by the solar energy, solar flux, they become O plus, right? And during nighttime, um, there will be some recombination. For example, the O plus, it will combine with the free electrons and become neutral oxygen ions. Or there are two steps of recombination that the N plus, will add with the oxygen dioxide, it becomes NO plus. And then this NO plus the free electrons become the neutral nitrogen and neutral oxygen, for example. So there are two parts. For example, therefore it means that the neutral oxygen ions, they come from two sources. One is from the ionized oxygen, the other is from ionized NO plus. Okay. So it's just the interplay of this ionization, recombination during daytime and nighttime that create all these ions. Okay, so because when we talk about ions, we talk about motions of ions and so on. So in the ionosphere, there are two types. There are two situations where we look at, right? One is the very um, well, for ionosphere, it's mostly ionized species that we're looking at. But because in the ionosphere, there are also neutral part, right? So in general, if you look at all this motion of ions and electric field, magnetic field, and so on, we look at two types of situation. One is a neutral condition. For the neutral condition, because it's interplay before of the ion motions, so sometimes we call momentum equations, and basically it's derived from the uh, Newton laws, right? For example, this is the second law of Newton. Just very simple summation of all the forces acting on a body is equal to the mass multiplied with the acceleration, right? But when we talked about iron, this is how it turns out. So basically, you have the mass. This is like FMA, right? So this is the mass density multiplied by the fluid velocity. Okay. So why do we call fluid? Um, well, because you have ions, even neutral ions, and you have so the speed, they sometimes call fluid velocity. I guess they just borrow from the physics, the typical physics term, right? So so one of the main momentum equations for the neutral ions atmosphere, this is rho multiplied with du dt, which is fluid density velocity, equal to the minus gradient of pressure plus rho times acceleration, but this is gravity, plus the constant value, and then so this whole thing is viscosity, like how how you look at the fluid, right? Some fluids like water, not much viscosity, but if you look at oil, it has more viscosity. Okay, and then this term I haven't looked at much, but they call flux density, and this is Earth rotation. So there are different forces that act on um, neutral ions, right? So the Earth rotation is one of which, and this one is electromagnetic force, which is the current density cross the magnetic field. Okay, you remember him? When he's still young, right? Okay, and then if you want to look at the similar equations, but more for ionospheric type or ionized type mediums, right? So it's very similar as well. Here we have the gravitational term, we have momentum flux, we have electromagnetic force. So for ionized ions, it's very similar. Okay, more note taking at all. I think it's good to take notes. It's important. Um, okay, so here we have different forces. So for ionized ions, or sometimes we call plasma. Okay, so sometimes you hear the word plasma very often. Plasma is like it can be fluid, it can be, but plasma is mostly this ionized state, right? That is not it can move around. It's not the neutral ions, so it has some fluidity to it. So we call plasma. Okay, but for me when I hear plasma, I just think of some electrons or ions. So that's one way of thinking at it, no? Yeah. Because when you talk about plasma, some people get very confused. What is plasma? It sounds very abstract, right? It's a little bit abstractual concept, no? It's plasma. But for me, when I think about it, it's just ions. So it's plasma. But I'm sure in physics, it means other things as well, right? Not just this. So anyway, so there are important forces that will act on your plasma or your ions. What are some forces that act on ions? Gravitational field, electric field, magnetic field, frictional field. These three they are very common. It's due to the gravitational acceleration. It's due to the electric field. Electric field acts on ions, and magnetic field velocity cross magnetic field. So you have all this acceleration, right? It's like the velocity pushes on the magnetic field. But the last one is a frictional. Yeah. Yes.
I'm thinking of maybe if
Motor. Think about motor. Yeah.
Coriolis affects
Second.
ionosphere.
Second.
If the Coriolis effect
Oh, I see.
affects the ionosphere.
Coriolis force.
Right.
Ah, I see. This is, yeah, you can talk about like that, but if you think about motor, what we do is, for example, how they create forces in some machine like motor, right? They just force this electron through the magnetic field, so you get force. That pushes through things. Yeah.
Because I'm thinking okay, the Coriolis affects the northern hemisphere different than the southern equator. So I don't know.
That's the orientation of magnetic field as well. Yeah. I mean north and south hemisphere, right?
Yeah, but the Coriolis because of the motion of the Earth.
Oh, I see. No, this is not the Earth rotation. This is the
magnetic field.
Magnetic. It's like the electron with velocity goes through magnetic field, so that creates some forces. But but you may ask what type of velocity, and well, wind can be one driver for this, right? Wind, or some types of like for example ions, they travel through magnetic field line, but that's different. But this is the force. For example, you have some type of tropospheric wind, that pass that pushes your electrons to travel. So when it cuts the magnetic field line, then you have this some sort of forces all over. But you may say, oh, doesn't winds come from Earth rotation? Well, you can say that, right? The wind in the world comes from Earth rotation, right? But wind can also comes from the changes between the difference between dusk and dawn as well. So that's also another. So when Earth rotation may be more generic, right? Okay. And the last one, which does not seem so clear at the beginning, but this is more like if you have many electrons, some of them goes to one direction, another goes to one direction, and they cancel out, they hit each other. This is what is called frictional force. Okay. So when all this comes together, it will update the momentum equations that we saw earlier. That on the left side is quite similar. You have the mass density times the differentiation of the electron density, the the J species velocity, and then minus gradient of pressures plus low JG. So this is for each species, right? If you have many species, you have many of these equations, and the rest is just similar to what we saw earlier. But the important one is here as well. So this term you have B cross B, right? But we can also have the effects due to the electric field in the ionosphere as well. So this is actually very important terms. We will see B cross B electric field all the time, and this is where it comes into effect other terms. And notice that in this equation, we ignore the viscosity and the momentum transfer term, so it's a bit shorter than the other page. Okay, and actually, sorry, this slide should come before the last slide. This is a complete equation set for the neutral atmosphere and for the ionized species. Or actually, you can say that this page is more like the summarization of the previous pages. And this is like a review of Maxwell equation of different laws related to what we talked about. So in Maxwell equation, maybe you've seen already in the past, no? They have the Gauss law for electricity, Gauss law for magnetism, Faraday's law for induction, and Ampere's law. I think if you read some of the paper, you'll probably see this quite often, which is a Faraday rotation and all that, right? Okay. You remember him? He's Maxwell. This layer, Ajahn maybe talked about it already. Daytime and nighttime, they're different, right? At this layer during daytime, you have F1, F2, you have E layer, you have D region. But nighttime, you mostly have F layer. You don't really see much in the E layer except the sporadic E events. This one let me pass, no? It's okay. This you probably have seen already, right? Okay. Okay, let's go. So one of the early observatory, of course, everyone knows that it is in Peru, right? Yeah, it's the Chicamaca Radio Observatory. Martin, have you been there before? Yes, of course, right? Okay. How far is it from the capital?
Like 2 hours in off road.
By road.
Yeah.
Is it in a remote area or it's actually quite a small, some city, like a city type, small city even?
Remote area.
Oh, I see.
In the outside of the city.
Ah, I see. I've never been there, but it's one of the places that looks very interesting to visit, at least once in a lifetime. Yeah. From Asia is a bit far to go to South America in general, no? Yeah. uh Anyway, so this is a picture of the location, the site. Don't believe me. This is most of the materials from this lecture. They're from the Kelly's textbook that I put it there already. Um, if you don't have the file of the textbook, I can send to you. Yeah, there are many chapters you can read through. Okay, but it's right at the equator, so it's super important. And so these some of the pictures of the station. They have what is called the incoherent radar, scatter radar, right? Or ISR. Okay, so it's very big with lots of antenna. It's not the same as in Chumpon. This is much bigger structure. It's one of the earliest big observation site in the world. So a lot of work from the 1960s, 70s, or 80s, they come from this site. Yeah. So lots of theory over there. So that station is called incoherent scatter radar station, and they can determine many parameters like plasma temperature, plasma density, plasma composition, ion drift density, and so on. And it can tell you at different altitude, right? So this is a bit different from at Chumpon, right? At Chumpon, you cannot tell the ion density, ion type information, but you can tell other things. No? Yeah. Okay. So one of the term that you may have heard before is called zonal drift, right? Or zonal ion drift, or some people call zonal eastward ion drift, yeah, which is the direction of the ionized uh, uh, ionized ions, or you can even call the electric field, okay, is this direction. So one of the formula here is the Vi is equal to E minus, this term you've seen before, no? And then this is the gradient. And the important term is here, which is the B term, which is the magnetic field. So basically, it's the interplay between the velocity and the magnetic field of this electric field. And they utilize the dropper shift concept. So for this part, it's quite similar to uh, the Chumpon radar station, is the Doppler shift. But the difference is, why can they measure more parameters like the plasma temperature, density? Because here we only draw one beam, but actually because they have so many antenna on the ground, they have multiple beams, yeah, that transmit to the ionosphere and reflect back. For the one in Chumpon, mostly we have 4 or 5 beams, right? But for uh, the ISR in Peru, they have many small beams. Yeah, so it's more refined and it's more detailed, and many direction at the same time. For Chumpon, you just scan, right, west to east, and that's it. But for ISR, it's like 3 dimension. I don't know, say 2 dimension or 3 dimension, but you have multiple beam, in depth and also left to right. So you have like a box of many beams, and that's why it's more detailed. And besides that, okay, there's some other reason as well, but let's take a look. So this is, have you seen this type of graph before? No, not yet, right? So this is one of the way to measure this type of drift, either the zonal drift or vertical drift. Vertical is just the altitude, right? But the zonal drift is maybe west to east, east to west. No? So this is one of the early data from M. Kelly's book, when they measure the drift, the eastward drift, uh, during local time. And in this picture, if you take a look here, um, so this line, so this is the sunset terminator, right? So this is where you have day and night time. So you find that during daytime, so you have one direction is negative, right? And then for nighttime you have a switch of direction. And in here they just look at different flux, solar flux value, less than 120 and more than 120. But in both cases, the situation is the same, right? Meaning that during daytime you have a certain direction. I think this is west direction, and then for nighttime then you have another direction, east direction, yeah, like a switch. Similarly, if you look at the vertical drift, vertical drift similar to the altitude drift, right? So um, so these are from different season: equinox, winter, and then summer. Okay. So this is the sunset line. Okay. During before sunset time, you have a drift. You don't have a very high drift value, meaning that the height of the ionosphere is not pushed up that much. It's just very constant. And then during sunset time, especially right after sunset time, about 1 hour, if you take a look down here, so sunset time, let's say here is 7 o'clock. So about 1 hour or 2 hours later, then you start to see this type of drift. Okay, of the, but what the drift of what? The drift of your I guess I would say altitude or height of the ionosphere, no? So they just drift up, you know. And this is similar to what we saw before. And I mean, besides that, they just look at different flux range of three ranges, you know, small, medium, and high. But for all these different solar flux density, you see this type of similar situation. And for this type of situation, maybe you have heard already, is called pre-reversal enhancement. Okay. You've heard of this word, right? Pre-reversal enhancement, or some people just say PRE, you know. Yeah. So when they say PRE, this is what it means. And all this information comes from Chickamauga station data at that time. Another term is called ambient perpendicular field. So you have the eastward drift, right? And then you also have another field that is perpendicular to magnetic field. Okay, I think you've seen this already. You know? So it's, this electric field is similar to the previous page. It's just the V cross B. Okay. So basically, there are different types of field, right? Zonal field, perpendicular field. There are many types of field. This is zonal field. Another one. Another look in the theory of this work. This is more like a top view. You look at the from the pole. You look down. So this Earth, you have two parts, right? The daytime and you have the nighttime, right? At the sun terminator, there are accumulation of electrons and ions. For example, at dusk, you have the dusk terminator, you have this ion electron accumulation, and then the dawn terminator, you have this type of ion accumulation. And this is the source of electric field, zonal electric field. Okay, so it's not due to the Earth rotation, it's due to the accumulation of ions and electrons at the terminators that causes this type of different direction. Okay, um, if you are not familiar, what is dusk? What is dawn? Which one is the morning time? Which one is the night time? Yeah, dawn is early morning. If you remember one temple in Bangkok called Wat Arun, in English it's called Temple of the Dawn. It's not Temple of the Dusk. And Wat Arun, the word Arun mean morning. Have you know Wat Arun, right? Yeah. It's the big temple next to the Chao Phraya River. Yeah. That's the name Wat Arun. Arun means morning. Then in English, it's not Temple of the Morning. They call Temple of the Dawn. Yeah. Anyway. And if you take a look here from the top view of the Earth, this is the magnetic field direction, which is from south to north, right? So you see like the tip of the arrow, right? So it jumps in from inside to outside the slide. So from south to north, okay? Anyway, so this electric field at night time it tends to be westward, and night and daytime tend to be eastward. And this the difference. So there's a voltage drop due to this electric field difference, between daytime and nighttime. This voltage drop or the voltage difference, um, they tend to be equal no matter where you are in the world. This is an example of the plots of the voltage during daytime and nighttime. So daytime the VGA is very high, but V night is the actually it's quite similar, but the ratio is quite constant, any time of year. So it's around one. So meaning that on this page, the daytime and nighttime voltage is quite similar. They're not that different. And what else? Okay, another one you may have heard is called F region dynamo, right? Yeah, the F region dynamo is related to how each layer of the ionosphere, they have some type of feedback loop or some circulation of electrons and ions. This is what we call dynamos, right? And we typically say that one of the driver of this dynamo is called wind, and you know that one of which is called thermospheric wind, right? And okay, what is thermospheric wind? This is from Professor Maruyama. Dr. Maruyama, he's the researcher from NICT. Okay, and he was in this area for a long time. In fact, he was one of the early person who went to Chumphon and Chiang Mai to set up the ionosone station. So he's been around a very long time. And in one of the study, he studied about the thermospheric wind and also the asymmetry between the northern hemisphere and the southern hemisphere. Okay? So sometimes we call thermospheric wind as neutral wind as well. So so now you understand, right? When you talk about neutral wind, what is neutral wind? It's the wind that carries the neutral ions, right? Because in the ionosphere you have more neutral ions than ionized species, right? So to move around the ionized species, ionized ions or electrons, you don't use wind. You use field or some source, right? But for neutral ions, wind is one of which to move around, right? So how does wind happen? So it's very simple, right? You have the sun, so you have the heating, right? So it heats one side of the earth, but then on the other side you don't have the sun solar heating, you have cooling. So that creates all the wind, that happens. And when we talk about the wind, it's not only the wind. Um, uh, it's not just the wind at the lower altitude. It can be the wind at 50 kilometers, 10 kilometers, even 100 kilometers, mostly, right? That you see all this wind. This is an example of the wind you can plot from the HWM model. Okay? You can download these coefficients and not coefficient, but maybe values. And for example, in this picture, this is the wind at the height of 250 kilometers. Okay? The x-axis is the local time, and the y-axis is the latitude. Okay? So for example, if you look at certain latitude, like the equator, for example, okay, so you see that this is local time, right? So during morning time, local time is what time? Let's say like early morning or 0 o'clock, like after midnight, right? So they will have certain direction, but then if you look at later time, like noon time, they will have like sort of opposite direction. So these are the thermospheric wind, or or neutral wind direction. Okay. At some latitude, it's not so easy to see, but where we are, it's very clear on the direction. And G once made presentation related to neutral wind from the Icon satellite, right? Yeah. So neutral wind in the Icon satellite is used to measure at about it's 400 kilometers, right? Yeah. They also measure as well. These maybe you see. This part I will not talk today because we have one lecture related to these parameters. I think it's in February, right? Another term you may have heard quite often is called equatorial ionization anomaly, right? Or sometimes we call EIA. So what does it mean? If you take a look at this picture, but this is from more like the side view, the equator is here. Okay, this is the northern part, like North Pole, say let's north direction. This is the southern side, right? Okay, so we have the magnetic field line from the south to the east, south to north, and then down to the south to equator and north. Right? And one thing you can observe here is that this magnetic field line does not just only come from certain point, but is actually an array of this magnetic field line that travels from south to east to north, right? So when you draw like with one or two lines, it's just like the depiction, just illustration, but actually there are many lines, okay? And another thing that should be observed in this picture is that oftentimes when this type of magnetic field lines moves from south to east to north, okay, so when it starts, maybe it starts at certain low altitude, but then it will move up to high altitude. So here is like the low altitude from ground, right? But then when it goes to near equator, it will be at higher altitudes. Higher altitudes. So it means that the magnetic field line, it initiates near the ground, which let's say you can 0 kilometer from ground, right? But then it will go up, to near equator and then go to the northern side. The altitude change. So in fact, you can think that the magnetic field line, they travel or they propagate from the 0 kilometer from the ground to the D layer, to the E layer, to the F layer, and come down to E layer, D layer, and so on. So the magnetic field line is the field line that connects different layers in the ionosphere. So if you have any ions that travel or pushed through the ionized ion that get pushed through the magnetic field line, these that ions will go through different layers before it comes back to the lower layer. Okay, you know what I mean, right? So if you have ions that are pushed through, it will go through D layer, it will go through D layer, it will go to F layer, come down to F layer, come down to E layer, and come down to D. So it's like the journey of ions, right? And that's how all these layers they connect to each other. Okay? So what do people say when they talk about the EIA? Okay, another term is called fountain effects, or another term is called Appleton anomaly. Okay, so basically what happens is near the magnetic equator, around here. Okay, the daytime eastward electric field will causes some type of drift upward. So if you take a look, basically, not so easy to see from here. Um, Basically, this is east, this is west. Look on the right side rather don't look on the left side. It's maybe a bit confusing. So if you look from east to west, okay, this magnetic field line will seems like entering the earth, right? So let's say you look the earth like this, okay, east to west, uh, this east, west, north, south, right? Okay, so if you take a look like this, it goes like this, and magnetic field line because it travel from south to north, so it looks like it's entering, right? Entering into the earth, right? So if you do the your rotation method, you get the drift up here, okay? So basically during daytime, what happens is there's a push of ions up here, so in up direction. So this is what we call E cross B. So when sometimes we look at this type of two images, they are different. One is looking at more from, this is can be still looked at as east west as well, but it's a different picture, you know. This is north south. It's like a rotation. But in this picture, north south is here. This is north south. So it's like you look at this picture, but you rotate to the left, you know. Yeah. Anyway, so this drift, what happens is, so during daytime, there's a push of ions from the equator areas, and then travel. So all these ions, they get pushed up, and then they travel down the magnetic field line. Yeah, I don't know if there's another page. Oops. Okay. So basically, it's like this: electric, the ionized ions, they get pushed up and then falls down to magnetic field line from the magnetic equator to about 15 degrees north and south of the Earth. Yeah. But some people just say that it's 15 to 20 degrees. You know? So it means that during daytime, if you measure the electron density at the equator, you should get less value than at the 15 to 20 degrees north and southern hemisphere. Okay. So when you analyze your data, for example, the electron density, you know, when we say that, oh, at the equator or at Chumpon station, we have high value. Actually, if you look at 15 to 20 degrees north or south, they should have higher values because of the EIA. So that means that when you plot this type of electron density plot, you see this type of enhancement around 15, 20 degrees at northern and southern hemisphere always. Okay? But there's this asymmetry between northern and southern of hemisphere, you know, so sometimes people uh, study on this as well. Okay.
This is what we experience with the ion delay.
Yeah, first this picture is actually IO delay.
Because when the satellite moves in the north to south or south to north, we see a different gradient.
Yeah, certainly.
Along the east-west direction, it doesn't vary too much.
I see. Yeah, certainly. So this is very common, you know, daily. Noon bite out. Okay, that's another term. Maybe you've heard of it before. Noon bite out. What is it? Well, if you measure some value like the FOF2, FOF2 is called the critical frequency of the F2 layers. Critical frequency of the F2 layers. Okay, and which is actually proportional to the electron density or NMF2 as well. If you plot this type of information like FOF2 or NMF2 values, sometimes there will be this type of called noon bite out dropped. Okay, so there's a drop of the curve around this area slightly, and then slightly slower to go up. And one of the main reason of this is actually related to the EIA, meaning that this type of dynamics occurred a lot during the peak noon time. Okay. Pre-reversal enhancement. Okay, now we hear again. Okay, some people talk about pre-reversal enhancement and the initiation of the bubbles. In that, if you look at the side view of Earth now, this is called side view. I think you've seen this picture many times, right? Yeah. So before sunset, the electric field tends to be eastward. After sunset, it tends to be westward. So what happens is you have the during before the sun during around sunset time, you have these type of changes of the sun of the solar energy, at the sun terminated areas. So so around this time, the electric field does not uniformly switch from east to west. Some is still eastward, some still west, some start to move westward. So it's like the place where water comes from different direction. You know what I mean, right? Comes to merge together, and then around that area you have some turbulence. So there's sometimes you have eastward direction, you have westward direction, and many of these. What happened with the driver from the ground, from the gravity waves, at lower altitudes? Then it drives up some type of bubbles or some types of depletion that causes bubbles around. When we say pre-reversal enhancement, which was evident when you look at the changes in electric field, before sunset and after sunset. So this is also what happened. So when we call pre-reversal enhancement, it means a pre-reversal electric field enhancement. Okay. Yeah.
It is like basically eastward, westward, before and after sunset.
Say again.
Because in the picture, the E bill is move westward before sunset, right?
Actually, what it means here is this is west to east.
Oh.
Yeah, but here it means that during that period, when there's instability, some areas have eastward, some areas have westward, and they are just jumbled up together. Like when you have water flowing from different directions when they meet each other, before they stabilize around that area, many direction, right? So it's not just uniform. So that's what it means. Okay? So that causes some areas of this is the bottom side, around 250 kilometers. Here it may be 100 kilometers. Here's maybe 300 kilometers. Okay, so at around this bottom side of the ionosphere, which is the junction between the yeah. So this is the region where you have the peak electron density. So that's where the bubbles or the fluctuation occurs more than at the other altitudes. So around this area, some area have uplift, some area have downward. So lots of forces all over the place, And finally, if it becomes severe with the driver from here, then it starts to ripple all over the place. Some of this type of instability region sometimes it doesn't materialize into the more ripples, so it just stops there. Right? Some becomes very severe, then it grows up, to more and more EPBs, for example. Yeah. And this instability sometimes is called Rayleigh-Taylor instability, okay, or they just call RT instability here. Okay, many works have described the linear growth of this type of instability or EPB. I think some of you have seen this type of formula before, right? So the linear growth or gamma is equal to EX over B. E is the eastward field divided by the strength of the magnetic field minus WY. This is neutral wind, and G over V in is just the ion neutral collision frequency. G is the gravity acceleration, and 1 over L is the scale length of the gradient. Okay. So if the scale length is very small, it tends to push to stimulate the instability more. So you have a small waves, a small wave, a small forces, all over the place. If the east field, if the eastward electric field is very strong, then you have a more growth as well. Okay. Magnetic field doesn't vary much in general. Okay, this is called F. Another term that you may have heard of is called F. Has Ajahn Lin talked about this before? Not yet. Okay, F region dynamo. Okay. So what is F region dynamo? Actually, there are two terms you may have heard. One is called F region dynamo. The other one is called E region dynamo. What happens is because the magnetic field line it goes through both the E region and then the F region, right? So this is the F, this is the E. Okay? So magnetic field lines goes through both the E region and F region and then come down. At here's the equator in this picture, and this is north, this is south. Okay, so it will carry ions and electrons, all over the place. So E region, and these are just multiple magnetic field lines. Okay, so there's some type of connection between these two lines, these two area. That what happens is, for example, during daytime, okay, during daytime, you have E region like a source of electric field, and F region acts like a load. So there are some connection between this line. It's like you have multiple current, in two wires. So there's some type of connection between, these few lines as well. And during nighttime, the the conductivities of the F region seem to be larger. So the F region will dominate. So you don't have the E region, so evident at all. Another picture, related to this F region dynamo, especially during the PRE, is from these pictures. So in this picture, you see that there are two areas. One is the daytime, the other side is nighttime, right? And so this is the E region, lower altitude. This is the the F region. Okay. So let's say during daytime you have the eastward wind. So the wind just go from east to west to east. So eastward direction. Okay. So right here near the sunset terminator. So this is where the transition occurs. So you have all these different direction of electric field that happens. Magnetic field is the same, no? Okay. So so in each region, for each altitude, you have this electric field. They all different direction, and this is where they all merge right here. The current density also during nighttime it tends to be very slow, very small, but during daytime, it has increased value. Okay. And before the reversal of the electric field drift, the eastward direct electric field tends to be enhanced around this time. So a lot of dynamics occur around here. at the terminator because of this the collision of different types of different forces, different direction of field and so on, and that's why there are often some instability in this region or in this area. Okay, so one question I want to ask, and you can think and or ponder about it. So why do bubbles occur in this area or in near equator rather than in other part of the Earth?
Because they have more energy of sun, control of sun.
Uh, is one reason,
Yeah.
partially one reason.
Yeah, because during the especially during the daytime, the particles are ionized, but during the night, and yeah, according to him, like at the equator, there is the high density of the ionized particles. So at the night time, that the recombination rate will be fast.
Sure.
And the one reason is we can see like the magnetic lines that drifts upwards in the equatorial region.
And the wind.
Yeah,
And the wind.
yes,
The wind is also west to east, east to west. You have like all these the perpendicular cross of E cross B.
yeah,
For example, you look at the wind in other regions, sometimes it's like all over direction, right? So that's why it has the maximum force.
yeah, that
Okay.
makes the
Magnetic field line is always north, south to north, right? But the eastward electric field, also the wind, is perpendicular here. That's why. Okay. And that's why you have the highest force that affects these ions at this region. Okay. Okay, this is okay. Okay, this one of this is the work from Mariama-san. He was talking about the atmospheric wind, and in his study he also talked about. So he talks about some other types of wind as well. No need to look at the first one. This is the same as we looked earlier. He talked about there are two types of wind that can occur. One is they call trans-equatorial wind. This is like the meridional wind, right? So this is called meridional wind. And another type he calls is convergent wind. Yeah. So sometimes you have a wind not just from south to north. I think this picture, this is south to north. But you have wind that comes both direction. So he tried to in this work he tries to look at why there's some asymmetry between the northern and southern hemisphere. So one factor that he talks about is the meridional wind as well. If you have different wind values, it also affects the distribution of these ions as well. This one I will pass. I will talk about this during later lecture. Okay, this is another picture that people often see. Is the bubbles, right? During their really instability, there's some fluctuation, and then we call this part as depletion. Depletion means that outside you have higher electron density, inside you have fewer, not fewer, smaller electron or ion density. You can think about air inside and pushed up, yeah. So it is severe. It is quite severe. It will, grows up to different altitudes, to higher altitude. Okay, And on the right side, basically it talks about how uh, this type of EPB or and also ions, they will travel through magnetic field line. Okay? And sometimes some people call field align, which means along the field. Okay? Another work is by Sunoda. He talks about um, he was trying to campaign more observation at different longitude of Earth and try to theorize, how uh, the large scale of the bubbles occur. So in one of the work that he talks about is um, this picture has a lot of details. Okay, one moment. So basically, he talked about if you take a look at the bottom side of F layer, let's say it's about 300 kilometers. Okay, and uh, and what happens is during the perturbation, okay, maybe it slowly you know wiggle, and then you start to have some type of primary bubbles occurs. They are called he calls this primary bubbles, like the top one, and then all these small one he called secondary bubbles that occurs. And so this is like a large scale type occurrence, and but these are small scale. Okay, small scale. The overall situation may last like very long distance, like maybe 1,000 kilometers. So these are like a large scale type fluctuation. And so that's why when we use observation, different types of equipment, sometimes we use scintillation to measure, sometimes you use some other types of equipment. You know, for example, if you use the scintillation index, we often say that okay, it's used to look at maybe smaller scale type of disturbance, like 100 meters type, right? Yeah. And yeah. So basically, what he was trying to campaign was that, the evolution it could be large scale. So it's important to do the observation at different altitude, at different longitude at the same time. And that's why CubeSats are used, right? And in some of the satellite, like Icon satellites, the satellites will go around the equators, right? It doesn't go north pole, northward, southward, but it goes around the equator to measure all this the information for this purpose as well. This is similar pictures that he mentioned earlier that these bubbles could occur at different altitudes. Sometimes um, if you have a weaker PRE, meaning that the drift is not so strong, you have bubbles at lower altitudes. For example, around here, like maybe 400 kilometers, it's not so high. Okay, but if you have the higher PRE, it's you could have the bubbles at higher altitudes, and so on. And this is at the equator. The distance between each bubbles could also be related to lambda as well. I don't know what this lambda is actually. No idea. I didn't observe this parameter before. I think it's the scale size. I think this lambda is like the scale size. But let me check later. But I don't think this lambda is about frequency or anything like that. because whatever frequency you observe is independent to how bubbles actually occurs, right? Yeah, I think it's scale size, but let me check. Yeah, it's in here. Yeah. Okay. Also, Abdul, long time ago, he also made some theories about the bubbles as well. And if you take a look in here, yeah. So this is the similar to the equation we saw earlier. So what is the driver? So in here he talks about ESF, but it's actually bubbles. But here it means equatorial spread F. So what does ESF or bubbles? How is it driven? What's the driving force? Okay. So one of which is the PREF layer that drives the ESF or bubbles. There is gravity waves from the ground. It's very low. It's like a sound like waves, very low speed, very low frequency, and this is one reason why when there are, for example, volcanoes or earthquakes, these very low frequency sound waves, it gets pushed up, to this layer as well. Okay, the PRE is related to the E layer, to the zonal wind, and so on. And then lower than that, of course, there are some gravity waves and so on, or tides that affects. Okay, so for the E layers, um, so for both E layers, it affects the PRE and the gradients at the bottom side F layer. It creates this type of instabilities. Okay. And yeah, something like that. Oops. So this is similar pictures that combines all this together. That talks about how gravity waves come up, and then at E layer you have secondary waves, and then it starts to affect the bottom side of the ionosphere. So similar picture. Um, some papers they try to simulate this type of bubbles. For example, in the work by Retter, is the simulation of bubbles in these layers. Another work is from Japanese researchers. What is his name? Sumoto, right? Yeah, from Kyoto University. He also works with this type of bubble simulation as well. I think it's a physics-based model. There are different types of EPB: post-sunset EPB, post-midnight EPB. Okay. Typically, we say that post-sunset, it occurs a lot during solar maximum time, and PRE dominates the ESF process. For the post-midnight EPB, this is typically said that more evident during solar minimum period, especially solstice months. But for the post-sunset, normally we look at the equinox months, right? And for post-midnight, the role of gravity waves seem to be more evident as well. This let me pass. It's already. By the way, the equatorial plasma bubbles seem to occur more at the equator areas, but for the medium latitude, they have some disturbance as well, but they call storm enhanced density. And this is not seasonal, not like EPB. Let me see what else. I don't want to go through application that much, but I will go through observation. Okay, so the different types of observation of the equatorial plasma bubble. Okay, for example, if you look at the satellite, okay, that depends on what sensor they use. And if you use V-shaped radar, it can go very small, like in meter scale. Ionoson is more point to point, no, because it vertical transmission. For GPS, when you compute the total electron content, it's like tens of kilometers. It's like large distance. For scintillation, it's smaller, so it's in like hundreds of meter scale. Optical sky imager is more like hundreds of kilometers because you look at the whole sky, right? And then for HF experiment, this is normally used for large scale wave structure or LSWS. Why? Because between transmitter and receiver, you can change the oblique angle and you can measure different places over a continent. So that's why there are different types of these things. For EPB, or in the old days, some people call ESF, how do they vary? Well, you can have long-term variation depending on solar cycle, F10.7, sunspot number. You can have more medium-term variation. You can even, this might be more like monthly. No? You can have short-term day-to-day variation as well. And not sufficient understanding, not so easy to predict. For example, if I want to ask you whether tomorrow there will be bubbles or not, you cannot tell. Maybe you can tell if you know that there are some storms, big storm, but not too super big. Maybe less than KP7 around that. Okay, it's likely you have storm for a few days, right? But can you tell whether how many days you have bubbles? At the moment, we cannot. This is open question, and it will attract a lot of attention if you can. I trans um, I shared one paper to Pimason some time ago, and I still haven't get some result from him. There was one paper from India. Maybe did anyone get this paper when I sent it last time as well? Yeah, basically they're trying to look at the relationship between bubbles and different types of parameters and see whether you can classify it. You not even use AI, but look at bubbles and the drift and this and that and even gravity waves coefficients and try to see the correlation. And from that paper, the results are very interesting actually, because it should be done before you even run any model or AI model to make sure that it's really important. Yeah. But the work was trying to say that even without using AI, if you can look at this relationship between bubble and 2 or 3 more parameters, you can tell whether you can see the clear relationship even without using any like AI model and all that. If you can predict this parameter, you can predict bubbles. So it's very good work actually. Yeah, it's from India. If I remember, I will send to you again one more time. Yeah. So for long-term variation, people look at how this bubble occurrence occur during each year, you know. So it's long-term, right? You can. This one I think is from optical sky imager. This one is more like a monthly type variation, but you can use ionoson, you can use TEC as well, right? You can, based on our TI, you can use all these things. Yeah. And let me see. So this is like the bubble occurrence, and this is the sunspot number. You just plot and compare. Yeah, I haven't seen this type of work recently. Someone should do it actually. It's interesting. In this case, the EPB is actually from satellite, so it's from the GUVI instrument. So I need to know. You need to know the height where you look at, because different heights see different things, right? If you measure at very high altitude, like 600 kilometers, you can do that as well. But you probably will get lower EPB occurrence than at 300 or 400, because some of the bubbles, when they occur, they just disappear. Some become strong and they go to a higher altitude. You know. Yeah. So even annual variation, you can see different months how they occur, and mostly you see that the bubble occurrence will tend to concentrate near the equinoctial months and during the March equinox and also the September equinox. So this is very clear. Of course, also depends if you are near the solar max, like about year 2000. This is the solar max period. You tend to have higher occurrence. Sometimes even like 80, 90%, right? Yeah, similar to what we see here as well. Yeah, someone should plot this type of graph. We haven't plotted this type recently. And so medium term, we talk about monthly seasonal scale. It has the dependence on the longitude, on the magnetic declination, solar declination angle as well. The effects of the thermospheric wind on the neutral wind, and you can talk about meridional wind as well because the is south to north, north to south. This will create asymmetry, in the values you obtain. Yeah. People who study about this, sometimes they study about the role of meridional winds on ESF. Sometimes it enhances. You could also have the suppression as well, especially during like solstice. You could have some suppression. Longitudinal dependence of EPBs. You can study. We have actually studied together with the team in Italy on how the longitude, affects EPB at different stations. At that time, I think we looked at some stations in South America and also some station in ASEAN, and we plot the result and look together. It doesn't give a very uh, in South America they tend to have uh, higher occurrence of EPB than in our area, yeah, because of the direction of the magnetic field line over there. We did this work in 2013, so at that time there were not so many stations, but nowadays now there are more and more. Yeah, I think some European authors they have worked together with 3 continents in the recent publication. So this is some of the work. You can look at the slide. It's not easy to see, but just trying to compare EPB occurrence in Chiang Mai, in South America, and so on. Just try to show. This is in South America. It tends to occur more. 2013 is the solar maximum. Yeah. But Chiang Mai is not equator. See, Chiang Mai is about 10 degrees, right, north of equator. So typically it has lower occurrence, less severe than Chumpon anyway. This is another work. I think it's with Professor Amory with the Vietnamese team, and they looked at data in South America and also in Vietnam. Yeah, and they show different parameters like occurrence, and they show monthly H prime F at these 2 altitude as well. Yeah. This is one of the classic pictures from Chicamaca radar, Peru. Yeah. What is this? Yeah, it's one of the very early picture in 1996. So basically, I think it shows some Doppler information here. Yeah, and so at different height, they converted Doppler information into sort of like spray depth or bubbles type pictures. That you can see all these travel and sort of like the plasma dynamics. At different altitude. Yeah, this is EAR. This one is at the Kota Tabang, Indonesia. It's called Equatorial Atmosphere Radar. It's a very big project. It looks similar to ISR, right? Yeah. And in for Kota Tabang, all these beams, they will face south, this area. This type of system can be optimized to have to go to higher altitude to look at specific E layer or F layer separately. This is from Nishioka. So this is some of the pictures, from the EAR in Indonesia. Yeah. So they look at bubbles at different time. You can see the red areas, and see how they travel from maybe west to east. Yes. When I first saw it, it looks like the X-ray plot or ultrasound images, no, like babies, right? Or weather type radar. This day you see all this picture, right? So someone should change this picture and make it even easier to see, right? Maybe remove background and then only see this type of thing traveling. Okay, this is from the EAR as well. Yeah, so the beams they go like this, go southward, in many direction, one at a time, no, not together at the same time. When they use this type of array antenna, they do it, especially this type, the one at Chumpon, the one at Kotorabang, you emit one beam at a time. But in ISR, I think they emit multiple beams in two directions. So this may be beam west to east, but ISR they beam south, west, south, north, south, east, west as well. So it's very interesting there. So this at the Chumpon station. The reason we install at Chumpon because we have already stationed at Kodorabang, which is at the EIA area. And Chiang Mai, we have ionoson genesis. This is like about 10 degrees north of in magnetic latitude. No, not here is the geographic latitude, but for magnetic latitude, Chumpon is about 2 or 3 degrees near equator, near magnetic equator. And Chiang Mai and Kodorabang is like the EIA region. So the reason why we install equipment here in order to see fresh bubbles. I emphasize the word fresh. We emphasize because if you measure information here and here, north and south, you see the grown bubbles, from the equator all the way up here already. Okay. Optical sky imager. This is another type of instrument. So we also have now we have three at Chiang Mai, Chumpon, and Koto Tabang. Basically, just take pictures and see this type of traces. If the bubbles occur, they look at the traces and see how they travel from west to east, for example. So this is very clear. Yeah. But this is, I think, is not from Koto Tabang. This is from Australia, right? Yeah. From somewhere in Asia, and then maybe from Japan, and then Australia. Yeah. So they also see bubbles, on the same day, but different direction. One is up, one is down. It's interesting, right? I don't remember that in this work do they theorize that the same bubbles travel to both sides or not, but probably because it tends to occur from equator and then go to higher higher latitude and lower latitude in the northern and southern hemisphere. Yeah. So that's why for this type of picture is very nice, and you could also look at, if I want to study more here, you could use some HF system, right, to bounce all this area and then see whether it happens or not. Yeah. This is Japan. This is Australia. In the middle, I think it's ocean. So this is like an illustration, from the work. This is from Otsuka. You Already this type of work we've seen. This is the picture at the station at Koto Tabang, like out of nowhere. 18 Yaki antenna, big station. Yeah. In Chumpon also big station, no? Yeah, we have to go down very soon. Yeah. Now there's a flooding situation in Chumpon area, you know. Okay, so this part let me not cover today because we have another lecture to cover these. Let me see, should I cover something else? This I will let and we'll look at later time, no? Okay. Another one, maybe this okay. The In the past, because we didn't have the GNSS receiver and all that, so in the past we look at ionoson a lot. So ionoson station was one of the earliest equipment to look at the disturbance related to the bubbles, and so sometimes you see the word ESF occur, often instead of using EPB, but it means the same thing. So there are different models to look at this type of probability. Uh, for example, in the IRI model, it's called International Reference Ionosphere Model. You can look at this type of model for many parameters. Let me see. Okay. For example, here. So one of the model called IRI or International Reference Ionosphere is a very well-known model that sometimes we download this data for use. So, so the IRI was actually the joint work between two organizations. One is COSPAR, or Committee of Space Research. The other one is URSI, or International Union of Radio Science. They're all very old. Okay, so the IRI model was developed out of the concept that um, physics-based model is very important but not sufficient at the time. So the IRI model is based on empirical type data. By uniting all the data that we collect all over the globe and then create single model to describe different parameters. And in a lot of these parameters, they're described in terms of monthly median and of electron density, electron temperature, ion composition, and so on. And for different location at different time, different sunspot number, okay. And I model can predict various parameters. We can come back to this later when we talked about the ionosphere, no? But what I want to share is, okay, let's go a bit more. The IRI model was built back in 1978, and they review the model every 2 years. So nowadays, even now, it's 2024, right? Now they have IRI 2020 model that just came out. Yeah. And in the IRI model, there are committee members from different countries. And I didn't even forget to put our names. So in Thailand, we have Professor Prasert from Industrial Education. Maybe you met him during the Oslo meeting. And I am one of the committee member from Thailand. Yeah. So there are many members, some already died, others just start to be accepted more and more, and from all the nations. So every year we have a session, we have a workshop called IRI workshop to present values from different countries, TC values, FOF2, SPEDEF, all these different scintillation, bubble occurrence and all, and present at this conference. And they go all over the world. There are the conference lasts 2 weeks, very long. 1 week is for training how to use model, and the students have to work on projects. And then during the second week is the actual conference. So second week, last day, the students team will present. Yes. And for each time we organize, I was committee and I was instructor on some years. Each year, let's say normally they accept about 30 or 35 students to start to get trained during first week. Every afternoon they have to work on data analysis as a team, and at the end of the second week, they present the total work. Yeah, and every time, let's say we have 8 teams, 4 or 5 teams get published in journals. Only 1 week of work, so very active students. Yeah, and yeah. Yeah. So next time when we have this work, this year we already had workshop, but unfortunately I didn't go. It was in Africa. Yeah. But next time I think it's gonna be in Korea. So some of you should apply, and yeah. So if it's organized in Asia, the organizer will give emphasis to Asian students to get trained and then work with other students from other countries. So next time. Also, there are some conferences coming up in um, One is called APRASC, and maybe there are other conferences as well. But look out for the scholarship for students. Yeah, because I think some of them have student application as well. No? So here I'm not gonna go through this much. Okay, let me go look at this instead. So one of the model from the IRI is from the website of the IRI. Oops, where is this? Let me take a look. Oh, here. Yeah. Okay, this is the page. Okay, so this is an example. If you can see well. Yeah. So if you go to the earlier page, this IRI model. Okay. Okay, let me tell a story a little bit about this. So previously, IRI model was joint work between COSPAR and USI, right? The main professor who studied IRI model, his name is Militza. Militza. So when we talked about this model or research work, we always have to give credits to earlier, people. Professor, what is it? Dieter. Is it Dieter Militza? Okay. He's already quite a senior actually, and very very nice guy, super nice guy. Yeah, yeah. He's from university called George Mason University, so he's quite senior, no? Yeah. So he works with physics and astronomy department. In this university called George Mason, it's not a very well known to us, to many of us, but in this area actually they built quite a very important department. I think they have at least 5 or 6 professors in this area in computer science and also in physics astronomy. Yeah. So anyway, I hope to visit him in the near future. Very very nice guy. So later on, the ARI model was adopted and supported by NASA. Yeah. So so for some years, the ARI model was hosted by NASA server. And lately, because in NASA, what happened is they started what is called Community Coordinated Modeling Center. I don't know if you have looked at this, but this is a huge thing. Yeah, the Community Coordinated Modeling Center, we all can be a member as well. And so basically, they have a simulation service, for different types of information. Let me see I haven't looked in this so much, but in this model, you can generate all these different values like ion density, TC, at different layers around the world, and you can look at different models as well. Yeah. For example, here this SAMI 2 Wacom X model as well. They also run IRI and so on. They do simulation. They do um, 3D simulation for you as well. Yeah, it's not from the real time data, but it's very very interesting. So please take a look in this center. They have a lot of things, but I don't know. I haven't used this much. But you can maybe simulation models. Let me see. They have run on request. If you run something very very long time and a lot of work, you can request and they will run and send the result to you.
Yeah, I already use it.
You try that. Okay. And they have the instant run. For short term, right? And if you run this model when you publish, I think they have a policy as well, right? Yeah. Is it you ask or you just acknowledge? Yeah, you have to acknowledge community coordinated modeling center. Because as you know, in our research work, sometimes we rely on other people or data baseline model, right? So you have to acknowledge all these important people all the time. Or some people who run simulation and use our data, they also acknowledge us as well. So it's both ways. So try to do that as a very normal thing when you make presentation. Always add the references, always, and give credit to people who come before you. And one day, younger people than you, they will give credits to you as well. So it's actually a commodity world. I had a meeting with the head of the CCMC earlier this year, and super nice woman. Kukai, or Kukai Konyanat. She was a Thai student in our lab. Later, she went to work at NICT, and later, okay. So Dr. Konyanat, last year she was working with CCMC as well, yeah, and I went to visit NASA to meet them. You know, let's see what else. Okay, I haven't tried to run this too much. Maybe you can give me more information later, but I can look at IRI first. Okay. So this version of IRI, to my surprise, is very different from all versions. Let me see if because it only has the one panel on the left, no? Oh, I see. Because on the west, in the previous version, I don't know if we can see the older version. Let me see.
But if we do like kind of request, you can see how to take it. It just has different kinds.
Yeah. It's like they're like automatic, right? Yeah. But anyway, so let me see. If you can choose model as well. Oops, no, not this. IRI version. Do they have different version?
We can change the version in instant menu, like you can choose 20 or 16.
Where? Oh, here, right? I think there's a version in here. Is it here? No. Just like the old. Anyway, so this is the old pictures, and so in the old days you can run online a different page. So in here, Professor Belisa and many teams, they talk about what type of inputs are there in the model. This is not AI, by the way. So a lot of these models, they use spherical harmonics model because it's global type models, right? You need the input of latitude, longitude. But in many of these models, the inputs that are required are generally the basic parameter like f10.7, like daily. They can use like the version of the like a smooth version of solar index f10.7, like 81 days, and 12-month running mean. Okay, and sunspot number, in this case they use 12-month running mean. So the RZ12, you don't use just raw data, you use the mean value. I remember when they were looking at this model, they were looking at different inputs into the model and see which type of average value is better. Another one is an anisotropy model. Actually, I don't know what this is, but I think it's related to FOF2 model, FOF2 values, and look at the delta, the change. Yeah, but I need to check what it is. Magnetic index, they use AP 3 hours. Wait, is AP 3 hours? Oh, really? Okay, and then they also use daily AP as well. Oh, they use KP. Okay, the indices are found internally. Okay, you can check yourself if you want. Then they have the optional optional value you can put in. For example, you can put in this model, you can put in like HMF2 or F2 peak height. You can put FOF2, you can put bottom side profile parameter B0, you can put FOF1, which we have not used much. You can put E peak height, E peak, and so on. Anyway, you can put electron density, range, or you can set the range, right? Daytime is 65 to 30,000, nighttime 80 to 30,000. Okay, also electron and ion density, temperature, 60 to 2,000 kilometers, ion composition, and so on. So all these have different models. They write using Fortran code. I think nowadays it's still Fortran code. We talked about changing, but who's gonna do it? Nobody does it. It's because this is voluntary basis from volunteer engineers, researchers worldwide. But there were some previous version that they try to run some programs and so on, or even Python, but they haven't decided to totally change. Yeah, it was the experiment.
Python 16 is working well, but I waiting version to Python 20, but they didn't publish yet.
Oh, I see.
Yeah.
Because it's all voluntary. But and there's also another network of Digison data. It's called IRTAM. This is from University of Massachusetts, Lowell. Mhm. So what they do is they have a lot of ionoson and other types of receiver, and they input into the server, and they generate this IRI This is what is it? This is but mostly FOF2 and HMF2, right? Okay, I will come back to this when we talked about models. Okay. But today I want to look at, okay, let's look at more information. So here they put link of different places like MIT, IPS in Australia, Kyoto. So all the people know each other in this field. When you see all these name institute, you know the face in your head coming out. They all like big community. I mean, it's a big community, but people know each other. And okay, here that's fine. I just want to give credit to people who start IRI model. So in this version, okay, what else should I look at? Basically, okay. So this picture, right? So so you can do either run on request, you can do instant run. What is public repository? Maybe codes. Yeah. So that's the code. Okay, you can select the version, but I wonder if you select the version here. Okay, that's fine. You can select IRI 2016, for example. So you can put the time, right? And you can put the dates. Oh, why did they set at 2012? That's strange. You can change this way, right? Okay, let's say today, 18. Oh, uh, wait, is this day, month, year, or month, day, year? Day first, right?
I think it's not because it was in February.
Okay. Yeah, because in US they use month first. So today now is 12 and then 18, right? And you just put whatever you put. Maybe put the past, not future. So here you can put in latitude, longitude. Where are we? What latitude? About 13.7, right? Longitude 100, 110, about 100, right? Yeah, height depending on what you want. But you can also put the range at the bottom, I think. For example, here, if you put the range of profile height, let's say I don't want to do it because I just want to look at certain height and I'm fine, like 300 kilometers, right? That's all. That's all. And then standard. Okay. So here's the list what you want, right? So okay, let's go with standard parameters. You can use optionals, I think. You can select what model you use, but let's go in this when we look at ionospheric parameters later. But let me see, should I add here? Okay, let me not put anything here then. Just stop the okay. Okay, add an option. Upper. Okay, here you notice that here upper height they fixed at 2000 and start at 50, which is the ionosphere, right? But I wonder why you set that storm enhanced, because in the old version they have place you can press storm enhanced, yeah, meaning that this value during very strong storm they change, right? So okay, electron density, oh, still height. Oh, height, not the. I thought they said at 300. Anyway, so here's the electron density at the different height, right? From 0 all the way to maybe almost 3 million electron density per cubic meter, you know, at different height. So the peak is around 400, 300, around here. And what else? Oh, this is NE over NMF2. So NE is the total, NMF2 is more like the electron density around F2 layers. Okay. What else? Temperature, you can look at the ion temperature. They have the ion temperature, and electron temperature and neutral temperature. So there are three. Okay. So you can see that typically electron density is higher than the neutral density, right? Because they have motions, they are momentums. And what else? These are the amount of ions, percentage of ions. So at around this area, O plus is very high, you know? And the yellow is NO plus and O2 plus. Okay, so the dominant ions here is O plus, right? At 200 or 300 kilometers. If you go to lower altitude, like around here, is the NO plus that is the dominant. Okay, and then if you go to above this 500, like 700 up, you have hydrogen ion H plus, and so on. So the dynamics at lower altitude and at medium altitude and high altitude, they are different, right? What else? Oh, it shows everything, no? Ion density for different types. The top one is the percentage. This is the density. TEC? Oh, no. This is strange. Oh, not no range of time. In this version, where do you set? At the bottom or? Oh, these are the values. No. Oh, there's a store. Yeah, you can use this option as well. I think you can set the profile type, yeah, to be time, for example, like hours a day. No, one to 24. No, I guess. Also, this version I haven't seen yet. It's quite simple looking. In the past, it's more like text, right? Many lines, right? Certainly, certainly. Yeah, old version you can do the same thing. So here is TC during daytime and nighttime. Oh, I see. Okay. Oh, but this is not in TechU, no? You have to convert it yourself. I see. So if you want this data, you can output two files, right? Or not here. Where? You have to go back, right? Here? Oh, I see. Oh, so this is like the old ways. I'm used to this. Oh, I see. And then you can just read it. Oh, and this is one file at a time, right? I remember students in the lab used to run using Fortran, not Fortran, but used to run like the the program itself. Can we still do that nowadays? Not anymore.
There is, I 2016 version for Python you can. Yeah, from MATLAB. But not 2020, 2020 is not updated yet, is for Python.
So if you want many data, how do you do?
For example, you can do request, like request. And
oh, request. Ah, I see. Like
summer,
runs on request, no?
Around like 2 years data, and same process for me around like 3 days, 4 days.
Oh, I see. Oh, you have to add like this?
Yes, like my affiliation name for mine is
Oh, I see. Okay, but it's still simple, right? You can say what year, and so it automatically runs for you. You can look at different models. Ah, I see. Okay. Oh, oh, so let's work for you because it's run on request. So it's less work for you, no? Yeah. Okay. Okay. So let's see. One of the tasks I want to assign you to. Let's let's think about it as information sharing, right? Okay. So for the information, you can get data from different system. For example, in ionosphere, you can do swarm, you can do gold satellite, you can do icon satellite, you can do cosmic satellite. Can each of you mm, work on this and then share us later on 14th January? What type of data is possible? What are the levels of data that you can look at, and then share? What we can get. You can also look at other types of model like the HWM model as well. It's also possible. That's for wind. Yeah. But when you bring it up, you download it, please prompt it. No? Maybe for IRI no need, no, because it's already done. It's not difficult. I don't know. Maybe there are some other satellites as well that you can. Why do I highlight this? I have no idea. Huh? Did I highlight this now? Okay. Okay, just click it, right? I see. So some of you maybe look at different satellite. Maybe can you tell me which one you are interested? Cosmic, one or two? Okay. What I'm interested is that what type of data that they give us, and how can we use this to determine different types of important parameters later, like EPB, sporadic E, you know, because for the basic or standard parameters, you can use it for plotting and all that, right? I think they probably give you like some type of SNR or signal level, right? Yeah, but then it would be nice to convert that to bubbles or sporadic E. Yeah, but you need to set some threshold and all that. So something like that. Or if there are some other parameters, let's see how how it works. Do you know which satellite you are interested in particular? BIM? You used to work with Gold satellite, right?
No.
Which one?
I use the data from Gray satellite.
Oh, Gray satellite. Oh, we can put in here. Yeah, but go in and look how to download some of this data and look together. Maybe share along the way. If there are some parameters we can look at together, maybe each system share, what we see. G, maybe icon satellite, no? Does anyone else want to look at icon satellite as well? We help G? Because G is already know some, so you can learn, no? Okay. So think of some satellite you want to look at. Yeah. Or others. I think there are a few more. No. And you may be interested, no? Because he also look at satellite data, but to convert to PM 2.5, and there are other types of data to share as well. Okay. Okay. Any question today? There's another set of slides. Oh, let me look at briefly with you. We have maybe 10 minutes now. Okay, this is the slides from Professor Amory. She's also very well known and very super nice professor. Oh, where's the paper? Let me see. I just downloaded it somewhere. Eh, Okay. I can go in here. Ah, okay, it's in here. Some of you have seen this paper already, no? Some time. Yeah. I'm not gonna go through all the slide because it has a lot of basic information. But let me go down to where I want to share with you. A lot of things are quite similar. Okay. Okay. Some of you have already worked with photoelectron content, right? There are various ways to derive it, but let's say it's GNSS or GPS data first, okay? And so this one, oh, it's about Nepal. So uh, on this slide, I think is the station in Nepal called Johnson, right? There's a station there, right? So this is the plot of whole year of data to 2009, 2011, 2014, and 2015. So very clear that during equinox, you see, high observed. Is this TEC or RTI? Let me see. It's a BTEC. I see. Okay. Yeah. So you see higher variation in vertical TEC during equinoctial months. I mean, nothing strange about this. And in here they also look at the asymmetry of the northern and southern crest at the EIA of the ROTI, for example. Yeah, people often like to look at the asymmetry study between northern and southern hemisphere and see which one is more severe or more values. Okay, so in one of the topics when she made the presentation, is about sun-earth connections. As you know that if you study, from Ajahn Lin earlier, he talked about various solar, solar terrestrial parameters. He talks about different phenomenon like CME or solar flares and all that, right? Yeah. Typically, when we study these, at least from our side, we tend to stay at the ionosphere layer, and then we don't worry so much about the upper layer. The most we looked at is maybe the geomagnetic storm, right? For the KP index and so on. Occasionally, when there are solar storm, maybe we look at the DST index as well, as part. But it's always well known that there's a sun-earth connection. There's a coupling between high and low altitude or latitudes always. Okay. So in one of these works, he was looking at some interesting terms called electric field PPEF, and it stands for what does it stand for? PPEF, pump penetration electric field. Yeah. Okay. So they talks about this type of phenomenon. When you have a large scale disturbed electric current. Okay. And also there's another phenomenon called electric field dynamo, DDEF. I think they will talk below here. So for electric field PPF, the parameter that we look at is dP2, and for DDEF, the parameter that we look at is called ddyn, ddyn. Okay, and so let me see. So this is the link between parameters that is a sun-earth connection. For example, during some storm day like St. Patrick's Day back in 2015, so if you look at the magnetic field line or DST index, you see that there's a drop of this type of values, right? Yeah, and then you during the active phase and during the recovery phase, then you start to see some slow increase of magnetic field values. In fact, this also related to the ring current in the magnetosphere as well. So some people study the impact of the start of the storm, which is called CME, and see how the TEC or electron density changes during this time. Okay, so this is very typical, right? How you merge them together. Let me see another one I want to look at. Okay, so in her presentation they were talking about two types of the phenomenon related to the current, electric current in the ionosphere. One is called PPEF, the other one is called the DDEF. Okay, so for the PPEF is the prompt penetration of magnetospheric convection electric field, meaning that during the storm, there's some type of very quick penetration of electric field to the ionosphere, and one of the parameter called dp2 is used in order to determine this type of dynamics or phenomenon. There are some papers in here related to this type of phenomenon. For DDEF, which is the magnetic disturbance from the pole to equator. So during this time, what happens is there's a delayed effect on thermospheric winds. So it takes time to reach the equators, sort of like a suppression. Okay, so when they look at the scintillation or ROTI, if you know ROTI or scintillation already, S4 index is just the index to determine the scintillation or fluctuation of the GPS signals. ROTI is derived from the standard deviation of the ROT, which is the change of the S-tech, and then how much they fluctuate, how the change fluctuate, not just the change. So one of the examples she shows is that for the disturbed ionosphere, when the storm is very, very strong, very often time the phenomenon, the dynamics in ionosphere is suppressed. And for example, they show that on March 17, 2015, I guess this is St. Patrick's Day. So you have ROTI plot. Red color means very high ROTI, and then suddenly it disappeared. So this is one aspect she shows. So there's some inhibition of scintillation, or inhibition or suppression, same word, of scintillation over the whole Earth during several days. During the May storm 2024, we saw a similar result, right? That on May 11 and May 12, nothing happens. Super quiet. TC is dropped, like a big drop, right? Another one is PPEF. In here, she shows the work in 2015 as well. There's a storm during solstice, also very, very strong. Yeah. And in this case, on this day, suddenly there's a big increase of the on 22 June, they're very strong enhanced of the electron density. So in this case, increased scintillation, PPF effect, short duration. Okay. And let me see anything else. This is the same as what we saw. They also look at this type of phenomenon from the RockSat satellite, that during PPF, during the storm, you see this type of increased, enhanced values, and during DDF, you see this suppression. So sometimes nothing happens, even with a strong storm. Okay. So I'm not going to go through this yet this time, but in the remaining slides, maybe next time I will go into this. They talk about how to compute dp2 and ddyn. Yeah. I remember in Oslo conference, one paper from Malaysia, the researcher was presenting on ddyn analysis, in Malaysia. So yeah, there's still a long part. We will maybe talk about it next time. But maybe this page I want to look at. Recently, I start to see some researchers. They look at relationship of various parameters like tech, for example. What is this one? Oh, this is DDYN. They look at the relationship even between ROTI and tech, compare with CME plus high speed solar particle, something like that, and the HSW event only. It looks like if you, when you maybe you ask Ajahn Lin later when you met him next week, during different types of solar storm, some storm are some storms are classified as CME only. Some storms are classified as CME plus HSW. Some storms are classified as HSSW only. Yeah, I think it represents high speed solar wave, so something like that. Yeah. Okay. Mhm. So, any question? Yeah, that's excitement, not difficult, no? Just this is just for fun. Yeah. But we will give you information more on this presentation next time. I think you should work on something that you are not already working on entirely. There's a twist or some other parameters that you look at as well. Okay. Next week, Dr. Lin, he will talk about magnetic field and KP index and so on. Yeah. He analyzed some local K index at Phuket station. Yeah. And then January 7, Dr. Acharapon, she will present on, I think that's a misspelling. It's supposed to be IGRF model and how to map some parameters onto the magnetic field line. And some of you may be interested. And that's it for the first half of the semester. It's very quick, no? Already almost. Oh, no class on December 31st. Oh, so bad. Anyway, yeah. Anyway, second part should be also fun as well. Yeah. Okay. Yeah, this semester we will try to look at the double layer model of TEC as well. Yeah, that has attracted attention recently. Okay. See you next time. Sure. Yeah, we haven't offered this course for some times, but then I realized that it's time to offer the course and maybe we work on something basic together. No?